Welcome back to this Intro to Machine Learning course from Pinata. Today we're going to cover classifier performance, both assessing and improving the performance of our model. We're going to cover how to assess the performance of a classifier, how to prevent the overfit of our model on the data, and then there's going to be an opportunity for you to try this out for yourself in a practical session. First up, how do we check the accuracy of our classifier? Before we jump straight into the measures, let's go over a key concept in binary prediction: true and false, positives and negatives. When we make a prediction, there are four possible outcomes. When we predict no and the answer is no, this is a true negative. When we predict yes and the answer is no, this is a false positive. When we predict no and the answer is yes, this is a false negative. And when we predict yes and the answer is yes, this is a true positive. True positives and true negatives are correct predictions, and false negatives and false positives are incorrect predictions. We use these outcomes to judge the accuracy of the model. Generally, we want to have the highest number of correct predictions, but depending on your problem statement, you'll want to use different measures of success for your model. There are three basic measures of success in binary classification modeling. Accuracy, which is all the correct predictions over the total possible outcomes. Precision, which is the true positives over the total number of the true and false positive results. This is the model's ability to predict positive instances that were actually true. Recall, which is the true positives over all the actual positive results. And this is the model's ability to correctly identify the positive result. If a false positive will cost you money, such as in fraud modeling, then you want to maximize precision. But if missing the positive result is too high a cost, for example, you're trying to predict the prevalence of a rare and life-threatening disease, then you would want to maximize recall. In general, we want to strike a balance between recall and precision, as problems are rarely balanced in the real world. You might think it would be a bit fiddly to calculate these measures by hand each time, and you'd be right. Luckily, sklearn has this for us. So for accuracy, you just import accuracy from sklearn.metrics. For precision, you import precision score. To implement each one is also very simple and intuitive. We use accuracy, precision score, recall score. But now we've built our model and assessed a few measures of performance, what about the dreaded overfit? Let's learn what it is and how we can prevent it. Now we know how to measure a model's performance, we need to learn how well a model performs in practice. We want our model to generalize to unseen data well, whilst maintaining accuracy. If the model is underfit, then it would generalize well to unseen data, but lacks the complexity to make correct predictions. If the model is overfit, then it is too focused on the training data and does not generalize to unseen data. The optimal model is a balance between the two, where it performs well in training and generalizes well in production. To achieve the optimal model fit, we need to split our data into at least two samples, one for training the model and one for testing the model. This ensures the model generalizes to unseen data, whilst retaining enough information to actually build a working model. The training and test sets both have to be representative of the population, and we use a larger training set because we want to maximize the amount of data that we can learn from. If you had recorded 1 million website visits, you might take 100,000 records and split that into 70,000 and 30,000 for your train test split. This should be sufficiently large enough to be representative of the population as a whole. The sklearn library makes this really easy to do in Python. First, we import the function from the library. Then we just use it to define our train test split for feature and target datasets. You can choose the proportion of data that you want to be training and set a seed for the random sampling so the results are reproducible. You'll do this for yourself more in the exercises. Now that we've covered the basic measures of performance and how to prevent overfitting with cross-validation, it's your time to give this a go practically. You can either work in the notebook that you used for the previous exercise, but we've also provided a link to a notebook just for this one. In it, you're going to split the data into train and test sets, use the training set to build a k-nearest neighbors model, and then you're going to score the model on the test set. Try to think about why the model performs as it does, both from a true, false, positive, negative point of view, and also from a practical point of view. What can you see? What might you do to improve? In the next session, we're going to bring all the things that we've previously learned together into one place, so we have an end-to-end modeling process. Then we're going to spend a bit of time on the practical benefits of converting your script into reusable code assets so you can use them in new projects without having to start from scratch every time. Finally, there's going to be a project where you can use everything that you've learned to build a classifier on a new set of data. This will be a good test to see how much you've been paying attention. And we hope you're enjoying learning with us. Thanks.